My name is Shanawaz. In this lecture, we are going to introduce the concept of primary decomposition, and we'll start this lecture with this definition of p primary components. Uh, let us consider a prime number p. So let p be a prime number. An abelian group G and abelian group G is p primary if for each element G in G there is an integer say n, which is bigger or equal to 1, with the property that with p to the n of G, so it must be equal to 0. Now p to the n equal to G means the order of the element G, this divide is the number p to the power n. So this further implies order of G is some number p to the power some number, some positive integer. So suppose if we have a group G, then a p, then an element G is said to be p primary. Then this G is said to be p primary if every element of G has order p to the power some positive integer. So if G is this given abelian group, then it is p primary component is defined as, so this is definition. So let us denote another definition, define another this is definition. So given an abelian group G, so it is p primary component, is defined as so it is p primary component, which we denote by G sub p, is defined as this GP is the set of all those elements in G such that p to the n of G is 0, where this n is bigger or equal to 1. That means all those elements of G whose orders are divisible, whose orders divide the number p to the power n, or in other words, all those elements of G whose orders are p to the power some positive integer, then GP is said to be p primary component. For example, if we consider the group, let us consider the abelian group G into V z mod 6z. So this group is not itself p primary, however it has p primary components. So the primary divisors of 6 are 2 and 3, so G must have two primary components. One is two primary component and other is three primary component. So this G, this contains elements which are given as 0 bar, 1 bar, so on, and 5 bar. Now note that each element here, this is a class of integers. So 1 bar are all those integers which when divided by 6 leaves remainder 1. Simply 5 bar are all those integers which when divided by 6 leaves remainder 5. So we claim it has two primary components. One is 3 primary component and other is 2 primary component. So G2, I mean the 2 primary component, that means G2 consists of those elements of G whose orders are 2 to the power something. So if we consider 0, it is order is obviously 1, so its order is as well to the power 0, so it contains 0 bar, because 2 to the power 0 times 0 bar is 0. Similarly, if we consider 3 bar, now 3 bar, because if we multiply 3 bar with 2, so this becomes 6 bar. 6 bar is nothing but 0 bar. So this G2 consists of only these two elements. Now let us look at G3 bar. G3, I mean, so it consists of 0 bar, so 2 bar because 3 2s are 6 and 6 bar is 0 bar, and 4 bar. So this is G3. Now so it has these two primary components, G2 and G3 bar, G2 and G3. Now it is an easy exercise to prove that. So this is an exercise, that is, if G is an abelian group, then the P primary component, P primary component, say GP, is a subgroup of G. So this is a subgroup of G for every prime P. So it is easy to prove this exercise, because if we have say two elements A and B in GP, now to prove A in GP is a subgroup, we have to prove A minus B is in GP. Now if A is in GP, so A is of the form so if A is in GP, this implies P to the power n of A is 0 and P to the power m of B is 0. Let us take K to be the maximum of m and n. So one can see here that is p power k of a minus b, that is a minus b plus a minus b plus so on plus a minus b, that this is pk times. Now g being abelian, we can write this as a plus so on plus a minus b so on minus b. Now this is pk times, this is pk times, so this is pk times a minus pk times b. This is same as pk times this is pk times a and pk times b. Now pk times a is 0 and pk times b is 0, so pk times a minus b is 0. So we have proved that this a minus b, its order is of the form p to the power some positive integer. So this implies this a minus b is also in GP. So this proves our claim that GP is a subgroup of G. Next we are going to prove a theorem which states that every finite abelian group G is the direct sum of its p primary components. So it has two items. Now this theorem is called the primary decomposition theorem. Primary decomposition. So it has two items. First item is every finite abelian group, finite abelian group say G is direct sum of its p primary components. And the second item is say we had two abelian groups G and G prime. They are isomorphic if and only if their p primary components are isomorphic. If and only if GP is isomorphic to GP prime, where this GP is p primary component of G and GP prime is p so this is GP G prime p. So this p is here. This is like this. So this must be true for every prime p, for every prime p. So let's prove the first item. So we have to prove G is direct sum of it is p primary components. So in that case we have to prove each element in G can be uniquely expressed as sum of the elements of elements from the individual the respective p primary components. So let us take an element, say x in G. Let x be in group G, and this x is given to be a non-zero. So this is non-zero element. Such that order of this x is, say this is D. Now D being a positive integer, by fundamental theorem of arithmetic, there are distinct primes, say p1 through pn, and positive exponents, say alpha 1 through alpha n, such that. So let us write here, by fundamental theorem of arithmetic, there are distinct primes, say p1 through pn, and positive exponents, say alpha 1 through alpha 1, such that this D is p1 to the alpha 1, p2 to the alpha 2, so on, pn to the alpha n. So this is by fundamental theorem of arithmetic. Now let us define this Ri to be equal to the D over pi to the power alpha I. So this is same as, so that this Ri times pi alpha I this is equal to T. So now this pi alpha I times Rix, this is same as pi alpha I, that is same as D. So this is dx, this is 0. So this means that this element here Rix, this is in the pi primary component. So this implies that this pi alpha I, this implies this Rix, this is in the pi primary component. So this is true for all I. Now it is given that these pi's, p1, p2, pn, they are distinct primes. So since p1 through pn are distinct, so these are the distinct prime divisors of D, where this pi, it does not divide Ri, because Ri is defined to be d to the power pi. So D cannot have a divisor which is pi. So pi cannot divide Ri. Similarly, P2 cannot divide R2, P3 cannot divide R3, and so on. So this means we see that these Ri's, they are relatively prime. We see that the GCD of R1 so on Rn, this is 1. So this follows from this definition of Ri. So since these are relatively prime, therefore there exist integers say s1 s2 through sn such that the linear combination s1 r1 plus s2 r2 is 1. Therefore there exist integers say s1 through sn such that s1 r1 plus so on plus sn rn, this is 1. Now this x is same as x times 1. Now this 1 is same as this sum here. This is I goes from 1 to n SIRI, because this sum is here 1. Now this is same as, so let's multiply this. So this is same as s1 r1x. So we can g being abelian, we can multiply x either from this side or this side. So let us take this x here, so multiply this from this side. This is s2 r2x plus so on plus sn rnx. So one can see here we have proved here that this rix, this is in the pith component of g. So this means this x is in g p1 component, this is in g p2 component, so on, this is in pn component. So we are halfway done. We have proved that this x can be expressed as sum of elements of these primary components. Now we have to prove this representation is unique. So to prove that, let us define hi to be the sum of all primary components except the ith component. So this ith component is omitted, so we have omitted this ith component. That is why we are putting a cap here. So hi is sum of all pi primary components except this pi component. Now to prove this representation is unique, it suffices to prove that. So to prove this g is direct sum of these primary components, it suffices to prove that it suffices to prove that the intersection of this hi with this gpi is singleton. So this is the singleton 0. Now to prove this is 0, let x belongs to this intersection. Now since x is in GPI, this implies their exists some integer, say L, which is bigger or equal to 1, such that this pi L of x is 0. Also x belongs to edge I implies, now since x is in this edge I, so x is in this sum, so this x can be expressed as sum of elements of these primary components except this pi. So x is sum of these yj's, while j is not equal to I, because in this expression this pth ith component is removed. So these yj, now yj being where this yj, this is in gpj, the jth component. Since now yj being in gpj, this means that pj power some number, say mj times yj, this is 0. Since pj power mj yj is 0 for some mj bigger or equal to 1 for all j, we conclude that t times this x is 0, where this t is defined to be where this t is the LCM of p1 m1 so on pn pm. So here this pi component is removed, so this is pi minus 1 mi minus 1, then pi plus 1 mi plus 1, and so on pn mn. This is the LCM of these. The reason being product of two numbers is same as the product of their GCD and LCM. So that is t is this implies this t is product of j not equal to I, pj mj, because these p I mi they are relatively prime, so their LCM is just their product. Now this t and this pi here, they are also relatively prime. Also GCD of this pi and t is 1, so there exist integers, say u and v, such that u times this pi plus v times t, this is 1. Therefore this x is same as x times 1, which is same as which is same as so this is upi plus vt times x because this is 1. So this is upix plus vtx. Now pix is 0 and tx is 0, so this is 0. So hence we are done. So this complete is approved.